Let's go ahead and take a look at the following. Let's say we had to solve this particular logarithmic equation and make sure that we only keep the good values that we get at the end that are such that if you plug back your potential solution into the original equation, which you see in front of you right now, that they do not create the log of a negative number or the log of 0, whatever the base is in this particular problem, because we know that such logs are not defined. So we'll have to toss out any potential solution that does not check in to the original equation. So first thing we notice is the following, is that we have two logs, and those two logs have the same base, and in this case it's a base 6. And we do have those two logs separated by a plus sign. So we have a sum of two logs. We do know there's a formula that we can use from condensing logs, which looks like the following. Sorry, this area is a little bit messy, but if you focus your attention right here, let's see what we have. When we condense two logs that are added to each other, notice if the base is b for both logs, and then you have a plus sign between those two logs, what can we do? We know that the sum of two logs is going to be equal to the log with the same base b of a product. And what do we have inside of this product? If the first quantity inside the log is m, then we will have that it's a log base b. When we combine them, log base b of we have log base b of m, a product m, and then m times what? Times what's inside the second log, m times n. So that's a key thing to notice over here. And whether you write it, vertically, notice that when you combine your logs, what happens is the following. You have those two logs combining as a single log base b. Now, because those logs were added, you have a product inside that log, and then the first quantity in that log, the first factor of this product is m, and the second one is n. So we're going to use this rule right now in our particular situation, and we'll combine our logs. So let's go ahead and see how to use this particular property. On the left hand side, you will have log base b, in this case it's base 6 of m, being added to log base b of n. And we know that those two logs are going to combine as a single log, log base b, of the product m times n. So let's see how this formula helps us. Now, if you take a look, the base b is the base 6 over here. So we will have those two logs combining as a single log. Now the base that we have is a base 6, and we have that it's a log of a product. Now what is inside this product? We do have the quantity m is going to be this quantity here. So we have a x plus 5, that's what m is, and that quantity m is going to time, it's going to time whatever n is. And what is n? N is just x. So I'll put for n, I'll put x, and m again was x plus 5. So we are basically condensing those logs as a single log, and that's equal to 2. Okay, technically we should put square brackets here, to be mathematically correct, but we get the picture. So again, we condense those two logs as a single log of a product. And let me just clear out a little bit all of those, formulas I had, so they're not in the way, so we can focus just on the problem. So let's now go ahead and proceed. So we have log base 6 of this quantity inside, and you can clean it up by distributing over here the x. So x times x is x squared, x times 5 is 5x. So it's really log base 6 of the quantity x squared plus 5x, and that's equal to 2. Now we do know that when we have a log equal to a number, we can go ahead and use a zapping of the log to see what we get. Okay, so the base 6 will travel to the right hand side, and this will disappear on this side, leaving us with what's inside the log. Again, it was a product of x plus 5 times x, which I expanded as x squared plus 5x, and that's equal to 6 raised to the power 2, 6 quantity squared, which is 36. So we have, let me scroll up over here. We have x squared plus 5x is equal to 36. We need to solve this quadratic equation, and once we get the solutions, we need to make sure that we only keep the solutions that do check out in the original equation, which is the one they gave us in the beginning. So let's solve this quadratic equation. Let's subtract 36 from both sides. And we have to solve x squared plus 5x minus 36 is equal to 0. So we need to factor this. To get x squared, we need an x and an x. Now we want two numbers after those x's so that the product is negative 36 and their sum is 5. So such two numbers are positive 9 and negative 4. So now a product is equal to 0 if either the first factor is 0 or the second one is 0. So solving for x, we get x is negative 9 or x could be 4. Don't just say, oh, I don't like negative values whenever I'm taking care of a log. You really need to actually plug in those values and see what they create inside the logs once you clean up the expressions in the log. And we need to stay away from any of those. Those are potential answers. They're not actual answers until we check them out in the original equation. And we want to stay away from creating, after we clean up things, a log of 0 or the log of a negative number, no matter what the base is in that situation. So let me rewrite my log equation underneath my potential answers, and we'll see which one of those work out. So notice that it's the original equation that we started with that I just copied below. And let's go ahead and try those solutions. Let me try first replacing x by negative 9 inside of that equation. So let's see, we would have log base 6 of negative 9 for x plus 5 plus log base 6 of x being replaced by negative 9. Is that equal to 2? I already see a problem here. Log base 6 of negative 9. When you are evaluating a log, no matter what the base is, you cannot have inside that log an expression that's either negative or 0. And we have two of them if you think about it here, so double trouble. If you clean up the first log, it's log base 6 of negative 4, which, is not defined, then we have another one not defined, so that's not happening. This log is not defined, this log is not defined, so you have undefined plus undefined. Is that equal to 2? You cannot answer that, okay, since those logs cannot be evaluated. So x equal to -9 is not an answer, okay, it's an extraneous solution, a fixed solution, so toss it out. Now our only hope is that x equal to 4 works out, and what we need to do is the following. If we use that equation again and we plug in a 4 for x, let's see what happens. So this will be a 4 here, this will be a 4. So we'll have log base 6 of x replaced by 4 plus 5 plus log base 6 of x being 4 is that 2. And let's see if that works out. So they're asking us log base 6 of 9 plus log base 6 of 4 is at log base 6 of 2. It's a little difficult for us to evaluate log base 6 of 9 on its own and log base 6 of 4. Which power of 6 gives you 9? You would be able to find that with a calculator, I would assume. But let's do this. Okay, since we have two logs that are being added to each other, they both have the same base 6, and both of those logs have a number inside of them that's not illegal, not a 0, not a negative. You can only do that if everything is behaving itself. So this is log base 6, keep the base to be 6 of, if you condense those logs, of the product of the first quantity inside the log, which is a 9, and the second quantity inside the other log, which is a 4, is that 2. So we're asking log base 6 of 36 is that 2. That's what we are asking. So if you think about it, which power of the base 6 will give you 36? 2 is indeed that, answer. So it is true, because log base 6 of 36 is 2. We get both sides to be saying the same thing. So our potential answer of 4 is really the true answer. So our solution set is only taking 4 in, and -9. No, we cannot take -9. It's not an answer. So only 4 is our solution here.